Hello, welcome to Physics 2211, Lab 5, Slinky. My name is Cole Appen. Introduction. The purpose of this experiment was to observe the motion of a Slinky drop from rest, then create a computational model and compare the predicted motion to the observed motion. Results. The observed motion and computational model differ, but only slightly. This is due to small errors. In a general sense, the experiment produces results that align with the computational model. Main physics principles. We will have Newton's first law: an object in motion will remain in motion unless acted upon by an outside force. Also Newton's second law: the net force on an object is equal to the mass of the object times the acceleration of the object. And static equilibrium. The bottom of the Slinky will be in static equilibrium at the beginning, while the top of the Slinky is exerting a spring force on the bottom. In other words, the spring force will be equal to the gravitational force, and the bottom of the Slinky won't move until the Slinky has collapsed. I just explained that the spring force is equal to the gravitational force at static equilibrium. Force equals mass times acceleration, and also momentum equals mass times velocity, and we'll also use the position update formula. Initial conditions. The system is a point mass at the bottom of the Slinky. Their surroundings are the earth, the air, and the rest of the Slinky. The initial velocity is 0, and then here's a free body diagram of the bottom of the Slinky at static equilibrium. Here's the tracker video. Here's the code for the computational model. The ball, or the system mass, has an initial mass of 0.218 kilograms. This is an estimated mass. And then it's an initial position of 0.467 meters in the y direction. Delta t was altered to match the time step of the video. And then if we move over to the right side of the code, the whole thing lasted 0.667 seconds. Basically, we have the net force being calculated on the spring, and then we apply the momentum principle to update the object's velocity, and then also update the object's position. And then this is the graph that the computational model outputted. As you can see, it's similar to the tracker graph, just smoother. Comparison of observed and predicted motion. The mass. The Slinky was estimated to have a mass of 218 kilograms, but this is an inaccurate estimation, could be an inaccurate estimation, as the mass of the actual Slinky in the video is unknown. In the tracker setup, I used the height of the man, which was about 1.75 meters, and this was used to calibrate the distance that the spring fell. This could also lead to inaccuracies in the data. Also, drag force. I did not include the force of drag in the computational model. This could also lead to some discrepancies. However, while the observed motion and tracker graph may have some inaccuracies, the overall shape, start, and end points of the computational model are quite similar to the observed motion, and you can see how they align. Conclusion. In this experiment, the Slinky of the spring was modeled as a point mass, where all of mass is condensed to one particle. Drag force is also considered as negligible. The spring has a fairly small surface area, so this would make the drag force not a huge problem. This makes calculations and modeling slightly easier. In the experiment, as the spring is released, the bottom stays in static equilibrium until the spring collapses fully and there is no longer a tension or spring force acting against the gravitational force on the bottom of the spring. Therefore, the net force is no longer equal to 0, and the system begins to fall to the ground, which is what you see in the tracker video. Here we have two free body diagrams demonstrating this.